Hello everyone. It's our great pleasure to have Dr. Bo Dong to give us the seminar talk today. And Dr. Dong is currently a visiting researcher in Princeton University, and his research is as topic Bioinspired computational imaging. And I know Bo since several years ago when we both work in Disney and ESPN, and so at that time he was working on player tracking and automatic broadcasting, and later Bo joined several different companies, including some very well known like SRI. Beforehand, he worked on SRI International, and even beforehand, he works on Kidware, and he actually has several collaborated with several researchers in our university already, like Andreas Salakis, and he has already collaborated with some of our faculties or members already, and Dr. Dong actually has beforehand he has already worked for several years, even when he was in China, and later he came to USA to obtain his master and PhD. His PhD is from is from
College of William Mary.
Okay, College of William Mary. Yeah, I always get confused with this name and several other private universities. And after that, he joined Disney ESPN and then joined Kidware and ISRI International. And until last year, he joined Princeton University as a visiting researcher, and he has published several very good papers in very top conferences and published journals as well, and like CPR and CGraph, which is very top graphics and computer vision conferences. And today he will, I think his topic is more about his recent research in conducting Princeton, probably some of his previous research on computer vision regarding his PhD and his jobs as well. Okay, well, thank you very much for coming here to give us the talk.
Sure. Thank you for the introduction. It's my great pleasure to be here to give introduction about my current research. I would say one branch of my research. A little bit different, like this research as conducting not with Princeton University, it's mainly with Chinese Dalian Technology University, because I'm also a research advisor at Chinese the Dalian Technology University, yeah. So which is an interesting collaboration. We collaborate since 2019. So today I'm gonna give a presentation mainly related to the project collaborate with Dalian Technology University. Princeton University participate on some ongoing efforts. I also gonna introduce here, but this effort is still ongoing, so I cannot give a lot of details, but this very exciting and interesting project. So I can start it?
Yeah.
Okay.
Yeah.
So today I'm going to give a branch, introduction about one branch of my research. It's called Bioinspired sensing and processing. Okay. So my research lies at intersection of computer vision, computer graphics, and machine learning and neuroscience. One research direction, actually, what I want to do is leverage bioinspired computational photography to enhance sensing capability of current sensors, especially in dealing with different degraded conditions. Another direction of my research, I'm interested in bioinspired machine learning, specifically in spiking neural networks, or SNN. SNN can deploy with on the neuromorphic hardware, which offers very high energy efficiency, which is desirable for energy constrained platforms such as drone, mobile robots. And of course, the third interest is that we want to combine this bioinspired sensing and processing to bring the big impact to the real world applications. Bioinspired theory or observation had inspired human being a lot in different ways. For example, we learn how to get better flight control from dragonfly wings. And also we learn different vision system from different insects, different creatures. For example, the mantis shrimp, this little guy down there, has a most advanced vision system in the world, which is very amazing. So the motivation underlying Bioinspired technology is this bioplausible theory and observation had been validated by nature at scales. This is important because when sometimes we propose some algorithms, we don't know really works. I mean, it works in small scales, but may not work in large scale. So this theory, if had been validated by nature for many, many years, millions of years, it works, right? So it means if we can really leverage them, it's definitely gonna, well, not definitely, well, I would say most likely gonna work well compared to we build some algorithm from scratch. Another key motivation to leverage Bioinspired or bioplausible theory is that one feature called homeostasis, which is the creature can have can simultaneously maintain a relatively constant internal environment, regardless what external condition looks like. That's very important feature we can learn from the creature because it can really provide great generalization for our proposed algorithms or sensing technologies. So that's basically my research interest. So now let's start my talk today. So one question I would like to ask you, have you ever think about why it's so hard to spot a fly? Sorry. Normally we spot a fly, we experience something like this. The fly actually can easily escape from us. And the reason for that is that the fly have very high flicker fusion rate. So flicker fusion rate is a metric to measure the speed at speech can process by brain. If you look at this flicker fusion rate, we can see the human being have only 60 hertz. However, the fly have 250 hertz. It means a fly can see the same motion 4 times slower than human being. Right? Then how about a dragonfly? Well, a dragonfly can catch a fly even at a very high speed fly, sorry, high speed movement. And amazingly, the success rate is more than 90%. It's not like a randomly catch the fly, but it's 90% success rate. Of course, if you look at the dragonfly's fusion flicker rate, is much higher than fly. That's why they can catch fly with this high success rate. Well, if we look at the dragonfly's eyes more closely, we figure out there's 3 interesting facts. The first fact is a binocular hyperspectral vision. Hyperspectral means the dragonfly can see much more color bandwidth compared to human beings, right? They can see ultraviolet light, they can see IR light. And also, since it's a binocular, it can sensing the depths. Dragonfly also, the eye is also sensitive to polarized light, which human being cannot sense it, right? And also it's extremely sensitive to motion, right? And also dragonfly leveraging all these cues together. So basically their eyes are multimodal sensing. Today's talk actually closely related to these 3 dragon eyes facts, especially on the sensing side. The first project I want to introduce is called depth-aware mirror segmentation, which closely relates to the depth cue we inspired by the, well, not inspired, right? That depth information is has been leveraged by different sensing technology for decades. But for this talk, we just correlate to this dragonfly facts, the depths. So the mirror, why is mirror? A lot of people ask me, why you guys interested in mirror? Because mirror gives some trouble to us, right? It's very common daily objects. But if without special treatment, the mirror gonna give troubles to our AI algorithms, especially for the reflective thing, we can misclassify or misdetect. Right? And also mirror can give some trouble to real creatures vision system. For example, this thing is called ghost blind. It's a widely used hunting equipment. And the hunters normally surrounding this ghost blind around them and make their target cannot see them. So in that case, they can make the prey in close range to to either shoot him or eyeball them. So the challenge for mirror segmentation is mirror do not exhibit a relative fixed patterns or slanted features. It's largely related on the contextual context environment, right? Because it reflects what the environment it stays in. So if we look at the depth map of the mirror, actually we can see interesting observation here is that we can see obvious depth discontinuities, right? And also if we see some mirror from another angle, we can see the depth information reflected by the mirror is also not their true depth, right? It's just depth what they reflect. So leverage these discontinuity cues, and also this depth variations also can correlation. We can leverage it inside the mirror and outside the mirror, because outside the mirror the depth is most likely is more stable, right? But inside the mirror sometimes it's not that uniformed. So that's why we can leverage this observation for mirror segmentation. That's what we proposed, PD-night. Basically, the network architecture itself is very simple. It basically just a unite. If we move the depth branch to this side, basically they have two encoder, each of them to encode the depth and the RGB domain, and then the decoder side is for generated the mirror mask. So for the encoder side, actually, we didn't develop any cool algorithms because we just want to extract these features. For the depth side, we're just using very simple 3x3 convolutional neural networks. It only have 5 layers. For the RGB domain, we just use ImageNet pre-trained ResNet 50 because ResNet pre-trained network have more context information from large RGB-based domain. So the network contains two major components. The first one is a positioning module, which leverages both discontinuity perception and the correlation perception, just I discussed. For the discontinuity part, we actually apply the same architecture to the RGB domain and depth domain and the RGB and depth combined domain. And each branch are exactly same, but they do not share the weight. So we can only look at one of them to understand the whole structure of these 3 branches. Intuitively, what we try to do is like for this first top branch, basically we dilated the convolutional neural network because we want to get bigger perception field. So we call this feature surrounding area. We call this feature basically can capture the surrounding environment features. The middle one, we just using 3x3 one. So basically we can regard it as a local feature. And the bottom one, we just use global average pooling to represent the global feature vector. So by contrast, the surrounding and local and the global and local, we have the enhanced feature for the surrounding area and the global area. So in that case, we can leverage this enhanced feature for the downstream processing. So that's basically the discontinuity perception branch did. For the correlation part, we are inspired by the self-attention module. Basically, specifically, it's called non-local. So non-local algorithm works pretty simple. So if we look at the bottom part, non-local because the self-attention, right? So to leverage the feature from the feature vector to generate 2 matrix. And then these 2 matrices come together and go through softmax, we can generate spatial wired attention map. And then we can apply this attention map to itself in order to achieve the self-attention. Since we have 2 domains, right? We have depth domain, we have RGB domain. In this case, if you apply the non-local or self-attention, we're gonna generate 2 attention maps. Naively add these two attention map together doesn't work well. It's because in different things, RGB domain and depth domain provide different cues. For example, in some cases, the RGB domain have a lot of correlation, especially when the reflection scene and the outside scene of the mirror have a lot of overlap. In that case, RGB domain provide more strong informative cues can be leveraged for the mirror segmentation. In some cases, the RGB domain do not, the mirror do not have overlap inside the mirror or outside and outside the mirror. So in that case, depth information play more important role. So these things is dynamically changed based on the scene setup. So that's why we propose a dynamically adding this two attention map dynamically. So in that case, we can deal with the scene dynamically to deal with these different Q contributions from these two domains. That's why we, instead of naively sum together, we generate a skew factor to balance the contribution from the two domains. So once we have the weighted sum together, then we have the attention map from here. And then we can use the combined feature vector and to generate another attention map to augment this feature map to enhance the feature map for the downstreaming processing. So that's the basic idea. The key here is dynamically attention scheme to merge two domain information. So once we have this initial position of the mirror provided by the PM module, then we can leverage the delineating module to refine the boundary of the mirrors. Since we have two domains, RGB domain and depth domain, and also we have the feature from the high level module. So this part, we just combine them together, which is similar to this continuity perception module. The only difference is like we ignore the global feature vector because the DM or delineating module mainly focus on the refined boundaries, which we can mainly leverage the surrounding area and the local area. We don't need to know the global area. That's why compared to discontinuity perception module, we ignore the global branch. So basically that's the idea of this decoder and also this basic idea of the PD-night. One thing we have to deal with is that because this PD-night or the proposed segmentation algorithm is a supervised learning, we need a data set for us to train. We collect the data set in a special way. We do not go out to using our own depth sensor to collect this thing by ourselves. Instead, we leverage existing RGBD data set. And we manually select the image which contains mirror, and we hire a third-party company to do annotation. In this way, we can guarantee the diversity of the scenes, and also we can guarantee the diversity of the sensors. Because if we collect the data set by ourselves, we probably mainly end up with a single depth sensor. But if we collect this data from different data sets, then using different sensor to collect this depth information, we definitely can enlarge the diversity of the sensing side. So the diversity is very important to build that data set. That's why we collected this this way. And also we can see at the moment, the data set is still the largest data set for RGBD-based mirror segmentation. The result looks very promising. We still get the best result. We compete with many other different approaches, for example, semantic segmentation, RGB-based salinity detection, RGBD-based salinity detection, and also we compared RGB-based mirror segmentation. All of them, we outperform all of them in a significant margin. And also we are interested in whether the depth information really play the role as we thought, right? So that's why we conduct an ablation study. So basically what we did, we just remove the depth branch and to see how the performance gonna be. Actually, once we move the depth, we can see the performance actually works as similar to the other RGB-based mirror segmentation. It means actually, even we have some special design for on algorithm side, but we can see the input actually play more important role. So let's provide another thought on research, right? Not only focus on the algorithm, also focus on input, how we can optimize input. Actually, that's one branch research for the Princeton, the group where I'm at, they are focused on how to optimize input instead of only focus on the algorithm side. This paper had been published in CVPR 21. We just described the challenging part for the mirror, right? It's because mirror can really mess up the AI system because they do not exhibit relative fixed patterns or salinity features. There are another object actually share the same challenging, which is also commonly observed is glass. Glass even worse, right? Mirror only reflect the light. Glass also the light can pass through the light and also have refraction and the transmission. It's also give harder time for AI system. For example, if we deploy the AI algorithm to, for example, master in this case, they will not output anything. Right? So this part actually closely related to the second effect of the dragon eyes is polarization light. Right? So what polarization light can do for us? Before I go to the project, let's first go through what's polarization light. I will introduce linear polarization light. I will not introduce circular polarization light because linear polarization light is more intuitive to understand. If you look at if you think the light rays as a waves, it consists of two fields. One field is called electric field, another field called magnetic field. They are orthogonal to each other. Polarization describes the orientation of electric field. That's why in this chart, I only draw electric field instead of drawing both electric field and the magnetic field. So when the unpolarized light passing linear polarizer, only the light with the same polarization angle can pass through the linear polarization light. That's why when the unpolarized passing linear polarization light, the light becomes polarized. If you look at this light ray from the front view angle, you can see something like this. So only the light variation in this angle can pass through this linear polarization light. All right. So this polarization light can be captured by a special sensor called polarization array camera or polarization camera. It's similar to conventional camera, but they put polarization array on top of the sensors. So if you look at the raw image they captured, it shares the same fair pattern as other conventional raw conventional camera. It's also RGB pattern, but under each of the color channel, they have four different polarization with four specific polarization angle, linear polarization angle, which is 90 degree, 45 degree, 135 degree, and 0 degree. So how we can leverage this four specific angle to help us to achieve the glass segmentation? Actually, there's one concept called Stokes elements, which can be calculated based on these four polarization light. Here, I'll only list the three of them. In total, there's four Stokes elements. S3 is more related to circular polarization. That's why I didn't list here because we only have linear polarization here. So S1 basically describes the total radiance we observed, and S1 describes the radiance with angle 0, and S2 describe the angle with angle 45 degree. With these Stokes vectors, we can calculate two things. Very interesting. It's called angle of linear polarization and the degree of polarization, or AOLP and DOLP. If you look at the AOLP and DOLP, we can see actually the glass now have textures. So hey, that's the key motivation to leverage polarization light for glass segmentation, because through polarization, the glass have intrinsic texture can be the intrinsic texture of the glass can be revealed by polarization light. Let's put it this way, and polarization light has been heavily leveraged by computer graphics community. Also, they mainly leverage the circular polarization to reconstruct the surface normals. But in our case, we just leverage as the intrinsic texture of the glass for help us to do the glass segmentation. Well, the polarization are wavelength dependent. That's why sometimes we see, and also angular dependent, right? So under some certain angle, and we can see in this case, the three color channel provide similar polarization cues. In some angles, they provide different polarization cues. And in some angles, we hardly see the polarization cues. That's why we propose our polarization class segmentation network, or PGS-NET. At the first step, we develop EDA components, which to balance the the different contribution from different color channel, because I just we discussed in some certain angles, the polarization have different cues, either similar cues or different cues or weak cues. So we leverage EAD or early dynamic attention to balance this contribution from different color channel. The AD is very simple architecture. Basically, we just make each of the color channel go through a resonant 18, and then we leverage the logic to generate the go through the softmax, and then we can and then I'm sorry, I'm just reading the chat. By the way, if you have any questions, please interrupt me. Feel free to interrupt me. So and then once we generate logic and go through the softmax, and then we can generate the weight to balance the different color channels. And once we have this weighted or AOIP and DOIP and RGB, these three domains can go through a backbone called coformer. Coformer actually it's I think it's developed last year, if I remember correctly. It's basically based on transformer brand, VIT network. So when VIT introduced to computer vision, they said, hey, we don't need convolution layers anymore, because we can leverage this self-attention itself can generate very good result. But later on, people start to argue that no, we still need a convolutional neural network to provide local information. What's a motivation for conformer? So basically what they did is like to combine both transformer branch, self-attention branch, which provide global information, and the convolutional branch to provide local branch, and then merge them together. So we leverage this, we adopt the conformer because it provides both global and local features, which is very important for us for glass segmentation. Right. So once the image goes through this coformer, we can extract this global feature and also local feature. So once we have the local and global feature, the first step we want to do is merge them, definitely, because they're from multiple domains, right? It's similar to the depth and the RGB domain. But now we have three different domains. One is RGB domain, another is AOLP, another DOLP. So we want to merge them together. So to merge them, we leverage the same technology, just cross-domain attention. So here, what we did is like, actually, it's a self-attention. Well, it's a global guidance attention. So what we did is we just leverage the global information and to generate reshape them and to generate, go through softmax to generate the weights, and to using this way to augment these local features. And then we sum together. So in that case, we can merge or fuse these three domain feature together. Well, our origin design, let's say we just using this combined feature for the downstreaming processing. We don't have this part. This part is called the multi-scale dependency perception. Then we figure out the results doesn't look nice, right? It's not good even compared to RGB based. And then we start to analyze why it doesn't work. And then we figure out actually the variation of the glass shape and the variation of the location really messed up our algorithm. Then we think, okay, so in that case, we need to introduce multi-scale perception system into the scene. So that's where the MSTP introduced to the work. So basically, it's also pretty simple stuff. Basically, we just leverage the adaptive average pooling to fix the feature map to 5x5, 7x7, 9x9, 11x11. And then we do a self-attention, and then we do upsampling to maintain their original feature dimensions. And then we concat them together and for downstreaming processing. And then it works well. So this multi-scale perception really play a role here. I hope this also can intrigue other researcher to develop a similar idea to leverage this multi-scale perception system. And then another part, actually, if we look at these things, it's a regular unite, decoder of unite, right? Basically, here we have the fuse feature and the go-to encoder, decoder. But the one thing the decoder is that the global information will be diluted if we go through more modules. right? So that's why we think, okay, since we already have the global feature from the conformer, why not we leverage this global feature to guide the decoder for the decoding process? That's where the GCG comes from. It's actually, since we have 3 domains, we want to leverage all the domains pairwise, right? So basically, we have 3 different domains. So this means we have 6 different combinations. So with this cross domain, the cross domain attention is also very simple. It's basically just the transformers attention, but transformers self attention. But here with cross domain, we just replace the query part with one domain and the key and the value part with another domain. The other thing is very similar to the self attention you leveraged by the transformer architecture. So with this global information and enhanced local features, what we can do is go through the decoder. I'm sorry. The decoder part actually have 2 attention. One is focused on the channel, another focused on the spatial wise. One thing I want to mention here, this part is a special design because in the transformer-based architecture, they normally use tokens for process, right? The VIT normally they do have they split the picture into small tokens, and then they add a class token as a special token to grab the global information from all the other input tokens. The similar here, because we are targeted segmentation task, that's why we just add a segmentation token here. So in that case, we can leverage cross-domain attention to enhance the glass tokens with the segmentation token. So that's basically idea for on the global guidance side, how to leverage the global feature provided by transformer based architecture. Again, it's a supervised network. We need some data set for training. But this time we are not lucky. We don't have an existing data set we can leverage to collect to ensure diversity because the trichromatic polarization queue can only capture by this specific camera. Nowadays, at this moment, I think only one data set besides us is called ZZU RGBP data set. But this data set is proposed not for glass segmentation, but it's for semantic segmentation. But it does have the glass class. That's why we can see if we extract all the glass class, it have 394 images. It's too small, right, to be leveraged for to validate our algorithm. So what we did is like we collect our own data set, and we ensured this data set collected from different scenes, internal, indoor, outdoor, from different scene setup. Basically, I asked my student go to IKEA in China because IKEA set up different rooms, set up these things. And we also go into different parking lot and to collect this data set. And we can see some distribution here of the data set. Some interesting audience can go to our website to get, oh, wait. Well, okay, but this data set is not released yet because we submitted the paper to CVPR 2022. We're still waiting for the result, but the review is pretty good, so definitely we're gonna get. We think we have I would say 95% getting for CVPR. So if you look at the result, actually, this is our approach, and this is our other RDB based approach. One thing I want to mention here is called the P-master RCN, developed by MIT Ramesh group. In their paper, they claim that trichromatic cues doesn't really help. So that's why in their paper, they only leverage a monochrome chromatic hue and the monochrome intensity, basically gray image and single color, single channel polarization cues. But our paper actually prove that trichromatic hue is more important compared to monochrome. And based on our ablation study, we definitely have strong opening, strong opposite opening of Ramesh group from MIT. But I think the reason for that is because we are more targeted on the large area. They more targeted on the small area. So that's why probably that's the difference introduced there. Okay, let's see. All right, so let's see the third fact of the dragonfly fact eyes is extremely sensitive motion. Actually, this part has been achieved by Bioinspired event-based camera. So it's event-based camera. I think probably a lot of students or professors not very familiar. So I'm sure some professor like will you definitely know what's event-based camera, but for general audience, I would like give brief introduction. What's event-based camera? Event-based camera is pretty interesting sensor. What they did is like they sensing the light changes in log scale. Once the changes in log scale over a threshold, it will trigger event. And this event is asynchronous. So it means as long as the event is triggered, it will output. Unlike the conventional frame-based camera, because we need to set up exposure times, right? Within this exposure time, the sensor expose to light and collect the photons and change the photon to electrons, and then go through very complex processing process, and then eventually we see a frame. And this frame output is synchronous, right? That's one big difference between event-based camera and the conventional frame-based camera. And if we accumulate these events in certain time period, we can generate a cumulative frame. So right? If we look at the cumulative frame, actually is the one in the middle. We can see we only can see the object are moving, right? For example, the building behind the thing, we cannot see it because they're static. The static object do not introduce light changes. So that's why in this specific case, we cannot see the building. But we still can see some noise around the corner, right? So that's basically event-based camera. Event-based camera has other interesting features because they have very high dynamic range with 140 dB. Regular camera only have 60 dB. Human being eyes is 100 dB. That's why we can see in this specific scenario, when the car drive inside the tunnel, through the event-based camera, we can see both inside and outside tunnel. But inside the tunnel, but the conventional camera can only see inside tunnel. Until you get out of tunnel, you can see outside. Sorry. That's one key feature we can leverage to deal with degree conditions, specifically for the high dynamic range thing. Another key feature, which is closely related to dragonfly eyes, because they are sensitive, extremely sensitive to motion. This means they have very high temporal resolution. Actually, the measurement rate for event-based camera can easily reach 1 million hertz. A regular frame camera normally we can see is 120 hertz. Of course, there's a high-speed camera can be leveraged, can also reach 1 million hertz. First of all, they are super expensive, right? Second of all, think about the bandwidth. Think about like you want to transfer a high res, like a 600 by 800 image, 1 million of the image per second. How much bandwidth do you need to have? So making these high-speed cameras not practically used for real-time sensing algorithm. But the event-based camera, since they only sensing the motion part, so bandwidth is much lower compared to this high-speed conventional frame-based camera. That's why we can also leverage event-based camera for dealing with these high fast motion things, right? In summary, event-based camera has advantages. Conventional camera has advantages, especially for synchronous frame, because I would say 95% of seeing a convolutional and a deep learning-based approach requires synchronous input as input, right? Only a few of them can deal with asynchronous input. So that's why asynchronous spikes or synchronous output from event-based camera really bring trouble to leverage, state-of-art CNN-based approach. And also, event-based cameras do not provide texture information. So why not we combine them together to leverage both advantages to do the object tracking? That's basically our motivation to combine them together to leverage both the advantage from both domain or both sensors. The way we do that is like we do not want to develop a new architecture from scratch because we think it's only about the feature parts, right? About input and the feature part. So the rest part should be the same as the original state-of-art network. That's why we just leverage existing single object tracking framework. In this case, we leverage the called ATOM, accurate tracking by overlap maximization, which is probably in CVPR 29. 19, I'm sorry, 19. So what we did, actually, we just adapt other papers, bounding box regressor or classifier. And what we did is like we introduced a new input, accumulate the event frame, and also we need to change the feature attractor accordingly in order to combine, to leverage both advantages from the both domain. So let's introduce how we can accumulate these events together, right? So give two frames. Actually, in between these two frames, we can also collect the events between these two frames. Actually, this has been leveraged by many different research at this moment, especially for slow motion reconstruction. So right? They can leverage the events between the two frames to reconstruct this latent frame. So in our case, what we did is like we just chop this frame, the events into n bins. In this case, we only chop them to 3 bins. For each bin, we just accumulate events together. So the way we accumulate it is like we just, for each pixel, we just select the events polarity with the latest timestamp. And in this case, we can accumulate 3 event-based frames. So in that case, we can change the asynchronous events to synchronous frame, and then it can be leveraged by deep learning-based approach, state-of-art-based approach, right? For the feature attractor part, of course, since we have 2 branch, since we're 2 domains, we definitely gonna deal with them separately. The ATOM framework require 2 feature vector, one for low level feature vector, one for high level feature vector. That's why we can see there's a L and H subscript here. For the feature attractor for the frame domain, we just leverage ResNet 18. The block 5 output we can leverage as a high level feature, and the output for block 4 can be leveraged as a low level feature, which is nothing interesting or nothing exciting here, which common design. For the EventBased Camera, since we separate the event to different bins and accumulate each bin to a frame. So this means we have an accumulated event frame. Since this event frame convey different temporal information, we don't want to waste any information. So that's why we propose using dedicated branch to process each of them. So that's why we can see each of the cumulative ones goes through a dedicated branch. Since we need to generate low-level feature and high-level feature, so basically just using the output of the first block edge attention block, and as a low level, and after second edge attention block, we leverage at a high level. The architecture of the edge blocks is very simple. Basically, we just first do the spatial attention and then do channel attention. That's it. Nothing more I want to introduce here. It's pretty simple. Since we have the motivation we want to leverage, so we want to leverage the advantage of both domains, right? So in that case, this means we want to adaptively merge them together. It's because in some things, for example, in the regular things, right? A regular conventional camera can provide very rich texture information, and it can be beneficial for object tracking application for sure. But in some case, in this case, probably want to leverage frame domain more. But in some cases, for example, in degraded condition, high dynamic range, the frame based conventional camera cannot really sensing anything because high dynamic range, but the events camera can still sensing things. In this case, we want to leverage more on the, we want to depend more on the event domain. So that's why we developed this adaptive cross domain. So for the bottom part, it's one branch we is introduced how we leverage the frame domain to enhance the event domain. On the top, actually, is opposite. See how we using the event domain to enhance frame domain. The architecture level is exactly the same. The only difference is input. That's why I only need to introduce one of them here, and then we can understand all other blocks. So the theory is also very interesting. So basically, to enhance the feature, we just want to leverage cross-domain feature vector. So in that case, we also leverage the multi-scale perception from the frame domain, and then to generate attention map to enhance the event domain. That's basically the first part of the equation. And the second part is just self attention, which leveraged by many other works. And the third part is just the skip connection, mainly for training stabilization. Once we have the enhanced feature from both event domain and the frame domain, and we can generate a weight, right? Because this weight is a balanced contribution dynamically between this event and the frame domain. So that's this small block, the highlight block, actually generated this weight. Again, the data side. So the data side is more challenging now because we need faster motion capturing, and also we want to conduct a lot of degree condition in order to show that the event-based camera can really effectively deal with degree conditions. Luckily, in the university I'm collaborating with, we have a VCon system, which is a motion capturing system. So what we did is like we deployed 21 different toys or small object into VCon system, and we plug the markers. So in that case, the VCon system can automatically tracking the object, and which means we can automatically generate the ground truth, which is pretty neat. But the limitation is that the VCon system can only set up the indoor. That's why the current object we collect is only focused on indoor at this moment. We plan to extend this data set for order, but in that case, we need a hire a third-party company for annotation purpose. Compared to existing data set, ours offers the largest data for training and testing, and offers the most diverse classes. The EED is too small, right? Only 179 frames. Probably is only good for proof of concept. EVIMO is a data set proposed by ETH, but this data set is not for single object tracking, mainly for motion segmentation task. But in any case, they only have 3 classes. Also, diversity is pretty low there. So with this, of course, we have the best result and significantly outperform all competing algorithms. Interesting, we want to show here. So even we simply naively apply the events domain input to the existing state-of-art algorithm, we can see the performance dramatically improve for the atom from 36.6 to 49. So that's huge jump, which means this events domain definitely help the conventional camera dealing with different degree conditions. And this is a some quality result. Remember, I just mentioned the weight to balance the contribution from the frame domain and the event domain. So in this case, it's a low light condition. This is one of the degree condition we generated. And we can see in this case, because the event-based camera still can see the object, that's why the weight on the event domain is much higher than frame domain, the same to here. And this is specific case, frame domain can be leveraged more. Here is because even it's a high dynamic range scene, we still can see the object from the conventional camera. In the event-based camera, we still can see the contour of this object, but we miss a lot of high frequency details. That's why the algorithm automatically changed the weight to leverage the event frame domain more. So basically the degree condition we construct actually is low light, high dynamic range, fast motion, which we can see the motion blur here. That's why we leverage the event-based domain more. We didn't see the motion blur from the event domain. And also, this also high dynamic range. Even though we can see the object through the frame, but we still cannot see, it's too dark, so I still have the high dynamic range problem. So that's why the algorithm will still leverage the event domain more. this is some video to show some result. And this paper published in RCCV 21st. All right. So I think I described the vision side. Now let's go to the processing side, Bioinspired processing. Specifically, I'm interested in spiking neural network, or SN. SN actually is a mathematical model to describe a biological neuron. So if you look at biological neuron, here I show a biological neuron. They have three important parts. First part called dendrite, and the second was axon, and then at the end they have axon tips, which connect to another neuron dendrite for communication purpose. So when the dendrite accepts some specs or information from other neuron, it changes internal called memory potential or memory voltage. So once the memory voltage exceeds a certain threshold, it triggers action potential. And that's how biological neurons to communicate with each other. SN actually did exactly the same thing. So which means SN need spiking threshold to mimic this action potential triggering process. Right? The problem here is that current SN, the spiking thresholds is either fixed or changing based on some heuristic rules, which is not very promising. And also we show that current SN suffers from poor generalization problem. But neuroscience scientists have studied the dynamic threshold for decades from different creatures in different nervous systems. Then why not we can leverage this theory plugged into the current SN to improve their homeostasis or to increase their generalization. That's basically what we did. This is still ongoing project. So that's why I don't want to give more details. Basically, the plan for this project, we want to submit to Nature next month. In high level, so what we did is like we leveraged two bioplausible dynamic threshold theory. The first theory is the threshold actually have the positive correlation with the memory potential, and another theory is the dynamic threshold has a positive negative correlation with the preceding rate of the depolarization, basically the changing of the memory potential. And these things existing on the single neuron together. So they so last part is hard to be modeled if you only want to leverage the heuristic PQ, because normally we just think, okay, there are only one relation, right? Either positive or negative, but actually they have two different correlations. We validate this because the key to introduce this bioplausible theory into essence is the key idea is to enhance their homeostasis and to deal with different degree conditions. So to validate this motivation, what we did is we probed three different degree conditions. We leveraged the host SN to control a robot to do the obstacle avoidance task. The first degree condition we introduced is we introduced dynamic obstacles into the scene. The robot trained with in the environment with only static obstacles, but in our cases, when testing the algorithm, we introduced dynamic obstacles, and based on our algorithm, it was pretty good. Degree condition, degree input is basically the robot leveraged the LiDAR, so basically the range reported by the laser rays. So what if we have malfunctioning laser, right? For some measurements are messed up. For example, we set up 0.2, this means this laser only become near sight, so I cannot see anything far away. Or we set 6.0, which is average range of the laser distance. So and also we can add some Gaussian noise onto the measurement to introduce a malfunctioning LiDAR. And also we can play some trick on the weight, introduce the degree conditions. Here's one result I can show you guys. Here is that we can see the blue color. So the small one is a robot, and the white one moving actually it's a dynamic obstacle. For this one, DT2 already failed, and this one gonna fail too, I think later. So that's how we see the performance of the optical avoidance. But if you see here, we report mean flare rate. The mean flare rate reflects the action potential, how fast they reflect the triggered action potential. It means if you have strong homeostasis, it means your internal potential is more stable. It means your flare rate should be consistent, right? That's why we can see the average rate is flat. This means our approach provides very strong homeostasis. And if you look at standard deviation, our approach also provides the lowest standard deviation. Of course, we test this algorithm with a more complex continuous control task. In this case, we also introduced the degree input to basically change the joint's velocity and position. And we also change the weight accordingly to introduce this degree condition to validate this homeostasis we introduced to the host SN. Okay, so let's come out under this my research of this talk. My long-term vision is like we want to leverage this process task I just introduced to bring the impact, leverage Bioinspired sensing and Bioinspired processing to give more impact to different areas of the different domain. Okay, that's it. Thank you so much.
Okay, thank you very much, Dr. Dong, for your wonderful talk. I actually have several questions, and but before my question, anybody from the audience have a question? Okay. Probably I first ask questions, and for the first one, and actually which is I mean the later that you for the event camera based SNN, and I saw you have simulation data, but also do you test on the real data as well?
You mean this one?
Yeah.
Yeah. So we are ongoing to do that because at this moment, if we want to deploy this SM-based approach onto real robots, we need the neuromorphic hardware, basically Intel Laoye. We applied, and they didn't ship to us yet. But what we did, we deployed this SM onto GPU, and we tested with the real robotic, and it works pretty good.
Okay. From audience. Do the event sensor work in a moving situation like moving car?
Definitely. That's an interesting question. Actually, I didn't mention that. As I said, the event-based camera sensing to the motions, right, is either ego motion or the moving target or the moving object. So the ego motion definitely going to trigger a lot of. So if you put an event camera on the moving car, it means all the background, static background become events, right? So in this case, make the event-based camera can be leveraged more complex. So what we do normally to deal with this problem is like we can do the motion composition, right? Remove the ego motion, or we can do the motion segmentation to segment the motion from the moving object instead of leverage the event from static objects. Yeah.
Okay, and probably a little bit related. So I saw you have tested on the event camera in combination with general color cameras, and you showed the result that even for some other framework that is just adding the event camera module that will enhance the results significantly. Have you tested single just based on event camera?
I'm sorry, what's the question?
I mean, have you also tested the detection result just based on event camera?
That's okay. Got it. That's a very good question. Actually, we have a CPR submission this year. It's only leverage event-based camera and combined with spectral neural network. In this scenario, we basically leverage the spatial information from the convolution, from the cumulative frame, and also temporal information from the event domain. Well, it works, but it doesn't work well because in some situation, especially for example, without any moving, either ego motion or moving target, you lose the cue. So that's one thing. Probably it's intrinsic limitation from event camera. So that's why I think we still need to combine event-based camera and some other sensor to do the job.
Yeah.
Yeah.
Yeah, that makes sense. Intuitively, that makes sense. One is something like detecting changing, another one is giving you more textures. That is good combination.
Yeah.
So another question from my side is, for the glass windows and you develop the algorithm, does it work also equivalently well for mirrors?
Ah, that's a good question. Well, that's basically our next project. The only problem for mirror is the mirror, how mirror reflect light is because there's thinner layer behind the glass, right? And the thinner layer actually is from different materials. Some use copper, some using silver, and they give actually different polarization cues, which is hard to be leveraged, except especially with linear polarization. But if we have circular polarization, that case can be easier to solve because circular polarization can change the direction of the rotation once reflected by the metal. But at this moment, we do not have the circular polarizer. I mean, circular camera, a circular polarization camera at this moment. But we can build one. We can just add a wave plate before one of them, and then we can generate a circular polarizer camera. But we didn't really leverage this part yet. But it's our research plan.
Okay. Okay. Also, in this work, I saw you have the filters that is oriented 0, 45, 90, 135 degrees. And have you ever tried to just using 2 degrees like 0 and 90 or something like using 3 to try to reduce the filter number?
Well, no. It's because if we want to calculate the Stokes elements, we have to have these 4 different angles. And also this camera is not made by us. It's actually a merchandise camera. So when they develop this camera, they just put this polarizer on top of their sensor. It's pretty neat design actually. But the best back to our question, we have to use in these 4 different angles in order to reconstruct these Stokes elements.
Okay. Okay. Yeah. And what is the valid range of your event camera?
I'm sorry.
The valid range, the sensing range, like 100 meters or 50 meters or 200 meters.
It's not limited actually. The only problem is because the polarization reduce half intensity of the light. We need a very large aperture size. So basically, it means the depth of sensing is become limited. The range actually depends on the lens. It's not related to the camera itself. But the point is like we want to we need to leverage a larger aperture size, right? Then this means if
that is actually I want to ask, if you have a bigger aperture, definitely you have more light to go through the aperture and capture those, and then you can detect what is the intensity difference, and that also depends on what is the shutter speed, and if you have higher shutter speed, definitely you can. So that is just not about. Probably not about your proposed method. It's just about my own question about the sensor that you are using actually.
That's right. I mean, actually, because we collect the data sets, right, and we also collect data set under different lighting conditions, especially for indoor parking lot. It's pretty dark in the nighttime, without the. I mean, even with the lighting on, still dark. Interestingly, it's like if you look at the polarization domain, even though you cannot see clearly from the RGB domain, right, you still can see some strong cues from polarization domain. So yeah, but definitely, as you said, if shutter speed is a problem, then it means that what we propose can be limited by some certain application scenarios, right? For example, cannot be deployed to some fast motion scenario. Limit to that.
Yeah, but I believe it's still better than color camera for most of the situations.
That's right. That's right.
A minor question. For the mirror of the window problem, I see most of your testing results are in indoor, especially for the mirror. Have you tested something? Have you tested something on outdoor, or do you observe there is some difference between outdoor and indoor?
Good question. The only thing limited us is because the depth in sensing. The depth sensor mainly works indoors, right? Because normally they use the infrared to project different pattern or time of flight to do the depth sensing. we didn't leverage like a LiDAR system to capture the depth outdoor yet, because as I said, we collect the data set through existing RGBD-based data set, which they collect mainly indoor. So back to your question, we didn't really test at outdoor scene, but if we have the depth maps, for example, from LiDAR, probably I don't think this algorithm will not work. Yeah.
Do you think there is some difference in performance?
Definitely, because if it's LiDAR, right, your depth map is much sparse, right? And but now we are using the very dense depth map. But I believe that can be with some special treatment can be dealt with. Especially there are a lot of research work leverage the sparse LiDAR for the dense depth map reconstruction. Sorry.
Yeah. A question from the audience as well. Event-based camera seems like a natural choice for SN networks. Do you see any exciting work going on in this field?
We are working on one actually. We submitted to CR 2022 this year. The review it's a 3 borderlands, I would say. So we hope our rebuttal can change their reviewers' openings. Definitely, that's definitely a very good point. Is because specking neural network can digest asynchronous input naturally. We don't need to do any special treatment. We can directly input this dynamics, asynchronous input specs into SN process naturally. So definitely that's our next step. Actually, we have another ongoing project to leverage the EventBased Camera for the motion classification from only one eye area, which can be leveraged by Meta worse, right? Like what we try to promote it. Yeah. Let's also leverage EventBased Camera and the SN together.
Okay, great. So any other questions from the audience? Okay. If no further questions, and thank you, Dr. Dong, for your presentation again. And like I mentioned, probably later we will post you a video on YouTube, so more public audience could learn from your presentation and could know a little bit more about your research, if you don't mind.
Cool. Yeah, no problem. Thank you so much, guys.
Yeah. Okay. Thank you. Have a nice day.
You too. Bye.
Bye.